Welcome to the Short Span Steel Bridge Alliance's 2020 topic-based video series. In this series, we'll review basic concepts and ideas pertinent not only to engineers new to short span steel bridge design, but those looking for a refresher of fundamental concepts. This video is part of a two-part series looking at live load distribution, a critical topic to short span steel bridge design. The goals of this video will be to provide an overview of the vehicular live loads used for bridge design, as well as to discuss structural analysis and live load distribution necessary for short span steel bridge design. We'll discuss the loads on bridges and AASHTO live load models, and then begin a discussion of structural analysis. We'll discuss longitudinal distribution and highlight transverse distribution. However, I should note that transverse distribution will be the primary focus of part 2 of this series on live load distribution. Also, it should be noted that this presentation is limited to AASHTO LRFD provisions and is being recorded during 2020. Please refer to all applicable state and local guidelines, as well as your current version of the AASHTO LRFD specifications to ensure that you're meeting current versions of applicable codes. When designing a bridge, particularly looking at a short span steel bridge, we have several loads that we need to consider. Typically, engineers will split this into two categories: permanent loads, commonly referred to as dead loads, or loads that remain stationary throughout the life of the bridge, and then transient loads, commonly referred to as live loads, or loads that move throughout the life of a bridge. In addition, we may also need to consider environmental effects such as wind or seismicity, depending upon your region. AASHTO LRFD specifications do provide explicit definitions of the loads that need to be considered, along with the associated load combinations and limit states. If we focus on live loads, particularly vehicular live loading, well, of course, we need to design highway bridges for some sort of vehicular live loading. However, it should be noted that cars don't really produce any appreciable load demand on highway bridges. It's the truck loading that produces the effects for which engineers need to produce designs. Specifically, the vehicles in question are what are called exclusion vehicles, such as concrete mixers or short haul vehicles. In other words, the vehicles that produce the worst case extreme effects. AASHTO LRFD specifications provide a model that engineers can use to simulate the exclusionary vehicular loading on highway bridges. This is termed the HL93 live load model. The HL93 consists of three components: a design truck, which you can see in the upper image, a design tandem, which you can see in the lower image, and a design lane, which is equal to 640 pounds per foot. It is the engineer's responsibility to place these loads on the bridge to produce the worst case extreme effects for a given design. And what we'll discuss here in a bit is how engineers would go about producing these worst case effects and how to go about computing them for your design project. One other point worth mentioning, according to AASHTO, the vehicular live load consists of a combination of either the design truck or the tandem, whichever produces the largest effect, and the design lane. In addition, the design truck or the tandem is augmented by a dynamic load allowance factor. It's commonly referred to as an impact factor. You can see the impact factors listed here on the slide. A couple points worth mentioning: usually most software packages will do a lot of these combinations for you. It's just important that you as an engineer understand the mechanics of the calculations that a particular program is performing. And also, again, as mentioned earlier, these provisions are related to AASHTO LRFD specifications. It's the engineer's responsibility to ensure that designs also conform to any relevant state and local guidelines. Now, there are several analysis tools and software packages available to engineers to perform structural analysis of highway bridges. These tools can use a number of analysis methods, ranging from basic Line-Girder approaches to more complex finite element analogies with two-dimensional or even three-dimensional analysis capabilities. However, for most routine short span steel bridge designs, a simple Line-Girder approach will be sufficient to accurately capture the behavior in order to produce a design. When using a Line-Girder approach, there are two main challenges in dealing with live loads that an engineer needs to deal with. And that is dealing with longitudinal distribution as well as transverse distribution. Longitudinal distribution means determining where to place live loads along the span in order to generate the worst case effect. Using a line girder analogy, longitudinal distribution is handled using influence lines, a topic most engineers are familiar with from undergraduate structural analysis courses. Here on this slide, you can see a typical influence line for shear and moment at a given section for a simply supported beam. If you recall from the theory of influence lines, an influence line is drawn for a single point of interest on a structure, and then worst case effects are determined using the resulting influence line. A natural question then might be, well, how many points of interest are enough? In bridge engineering, it is typical to generate influence lines at 10th points along the span. So for instance, if a bridge is 50 foot long, an influence line is drawn at 5 foot increments along the span, and maximum moments and shears are determined using those influence lines drawn at those 10th point increments. Once the moments and shears from an influence line girder analysis are obtained, they then need to be distributed transversely. What that means is determining how much live load is transferred to each girder. After all, bridges are three-dimensional systems. Longitudinal distribution tells us the maximum moments and shears along the span, but we then need to determine how much of those moments go to each girder. Fortunately, AASHTO specifications provide a tool for us engineers to perform that transverse live load distribution, and those are called live load distribution factors. What we do is we take the moments and shears from an influence line analysis, multiply them by the appropriate live load distribution factor, and we then obtain the live load moments and shears necessary for design. Part 2 in this video series will specifically discuss live load distribution factors and how they're computed according to AASHTO specifications. One software tool that is worth mentioning is LRFD Simon. This is a software tool produced by the National Steel Bridge Alliance that you can find at the link shown. It is perfect for bridge projects that don't require a 3D finite element model, such as a short span steel bridge, and it is a complementary resource for bridge engineers to use. We highly recommend that you download this and use it on a representative short span steel bridge design project. A couple of other resources relevant to this topic. The National Steel Bridge Alliance produces a steel bridge design handbook, and there is a chapter specifically dedicated to structural analysis, as well as the Barker and Puckett textbook on the design of highway bridges provides a very nice overview of the structural analysis models, the different two-dimensional and three-dimensional analogies discussed in this video. This concludes part 1 of our discussion on live load distribution. Part 2 will again discuss transverse distribution and specifically look at live load distribution factors. Thank you very much, and we look forward to seeing you in our next video.